First, we will continue chapter 17. Chapter 17 is on interpolation. We have introduced yesterday polynomial interpolation, and we have seen that it's not very efficient for large dimensions. So for large n, we will have high errors, round-off errors. This is why we introduced last time Newton interpolation as an efficient method to perform interpolation. And now we will introduce a new method, which is Lagrange method, which is as efficient as Newton, and it will provide same results of Newton. Okay? So what is Lagrange interpolating polynomial technique? It consists on defining the interpolating function as a combination of y data. Okay, so with coefficients of these y data that will be interpolating functions. So for example, we will start by the simplest interpolation, which is linear interpolation. So if you want to use Lagrange method to do a linear interpolation for f1x, we write f1x as combination of summation of two terms, one multiplying y1, one multiplying y2. So here, since you have just 2 points, your your function, your interpolating function, will be the summation of two functions multiplying y1 and y2. And these functions are the Lagrange operators, and they will be linear functions when you want to do linear interpolation. L1 and L2 and L3, let's say, will be quadratic functions if you are doing quadratic interpolation, etc. So if you have to do a linear interpolation, you just have two data points, and you will need two operators, L1 and L2. Now, how to define these operators? These operators will be defined according to the definition of the interpolating function. You know that the main condition of the interpolating function is that it should pass by the data point. So we can write that for f1x, for x1, and if I put f1 x1, I should obtain y1. This means what? If I compare with my Lagrangian expression of f1x, L1 should be equal to 1, and L2 should be equal to 0 when x is equal to x1. This will define for me the operator L1. So L1 should satisfy two conditions, and it's a linear function. So once I know these two conditions, and I know that it's a linear function, since I'm doing linear interpolation, then L1 is 1 at x equal x1, and L1 is 0 at x equal x2. I can define my linear function. And we will see together what is the form of this operator. Now, similarly, how to define L2? L2 definition will come from the second condition. So the second condition is that for f1 at x2, I should obtain f1 at x2 equals to y2. This means that I should, if I compare with my expression, when x is equal to x2, I should have now the inverse. Now I should have L1 to be 0 and L2 to be 1. Okay? So now this is my results. So this is what define my operators L1 and L2. Now we will see what is the form that can satisfy these conditions, having L1 and L2 linear. According to this definition, I can come up with the following form for my operators. For L1, I will define it as a linear function of x, such as L1 is x minus x2 over x1 minus x2. Let us verify together that L1 satisfies the conditions. So the first condition is that L1 should be equal to 1 at x equal to x1. And this is verified here because if you replace x by x1, what will happen is that you will have x1 minus x2 over x1 minus x2, which will give you 1. So the first condition is now verified. The second condition is that L2 should be equal to 0 when x is equal to x1. Now, if you replace, here, L1 should be 0 when x equal to x2. So when I replace here x by x2, it's verified that x2 minus x2 will give me 0. So this function will verify both conditions for L1. Now, for L2, same procedure. For L2, the conditions are, it should be 0 when x equal x1. And if I replace x by x1 here, I can verify that this will give me 0. While when I replace x by x2, I will get x2 minus x1 over x2 minus x1, which is 1. So also the second condition is satisfied. So I can conclude that I can have a certain pattern, okay, to define L. Yani now, if I tell you I don't want a linear interpolation, I want to do a quadratic interpolation. If I want to do a quadratic interpolation, then my function will be of second order. So I can write that f2 of x will be equal now. Since it's a quadratic interpolation, I need 3 data points. So I need x1, y1. This is the first point. I need x2, y2 as a second point. And I need x3, y3. So my resulting Lagrange interpolating polynomial can be written as a combination of my y data. So L1, y1 plus L2, y2 plus L3, y3. And similarly, I will define my operators. So as you can see, F2 is a summation of functions that where L1, L2, L3 are the weights of y1, y2, y3. And when I am doing a quadratic interpolation, then L1, L2, L3 will be quadratic functions. And I will define them in a similar pattern. So I will put what are the conditions. Let us think together. What are the conditions? I want that when I put here x1, f2 of x1, I should obtain y1. So what will be L1 then? What should be L1 in this case? Yeah, who will tell me what will be L1? I should have L1, L2, L3. Yes, Leah, very good. L1 should be 1, and L2, L3 both should be 0. So very good. So when x is equal to x1, L1 will be 1, L2 will be 0, and L3 will be 0. While when x is equal to x2, L1 will be 0, L2 will be 1, and L3 should be 0. And finally, when x is equal to x3, L1 should be 0, L2 should be 0, while L3 should be 1. So this is how I define my operators, my Lagrangian operators. So now, here, this is the case of a quadratic function. So if I want to do, this is first the case of linear function. So when it's a first order, as we said, when the function is linear, first order function of x, both L1 and L2 should be linear functions. While if I want to have a quadratic function f to x, then L1 and L2 and L3 should be second order. So this is what we will see here. So now if we want to define quadratic second order Lagrange polynomial to interpolate a function, then it will be the combination of L1y1 plus L2y2 plus L3y3. And as we mentioned together, the conditions for L1 are the following. It should be 1 at x1, 0 at x2, 0 at x3. While L2 will be 1 at x2 and 0 at x1 and x3. And finally, L3 will be 0 at x1, 0 at x2, 1 at x. Now, how to define these operators? It's very simple. Same method. I try now to find, instead of a linear function, it will be a second degree function satisfying these conditions. So let us see the following form. So always we have at the numerator we'll have products, and at the denominator we will have products. At the numerator we will put, when it is L1, we don't put x1 al numerator. We will see why. Because if I do now x minus x2 times x minus x3, and in the denominator I replace x by x1, this will satisfies the conditions for L1. Why? Because when x is equal to x1, I will have here x1 and here x1. This will give me a ratio of 1. And then when I have x equal x2, this term will be 0. So this will ensure that L1 is 0 at x2. And when I replace x by x3, this term will be 0, which will ensure that L1 is 0 at x3. So now, this is the general way of doing it. So now if I want to find L2, it's the same procedure, but now in the numerator, I don't use x2, I do x minus x1 times x minus x3. And in the denominator, I replace x by x2, so I get x2 minus x1 times x2 minus x3. While for L3, I don't use x3 in the numerator, I do x minus x1 times x minus x2. And in the denominator, I just replace x by x3. So I get over x3 minus x1 times x3 minus x2. So now you can conclude that you can generalize this result by saying that if now I want to, this is for quadratic interpolating Lagrange polynomial. Now if I want to do a cubic fit, what should I do? Who will tell me what will be L1 for a cubic interpolating Lagrange operator?
بيكون فيها كل شيء إلا ال x1.
اوكي يعني L1 شو بدي زيد عليها هون؟
x minus x4.
Yes, very good. مين عم يحكي جورج؟
Yes.
Okay. So it's x minus x4 over x1 minus x4. Okay. And now L2 will be x minus x1 times x minus x3 times x minus x4 over x1 minus x4.
مش x2 minus x4.
Sorry. هون yes. Here x2. Okay. So x minus x4 over x2 minus x4. And here it will be times x minus x4 over x3 minus x4. And what should I add now to these operators? I should add L4. Okay. L4 will be, what will be L4?
X minus x1.
Yes. X minus x1.
Times x minus x2.
Yes.
Times x minus x3.
Yes, very good. Over now, I just replace x in the denominator.
x4.
Yes, exactly.
Yes, x4.
So x4 minus x1 times x4 minus x2 times x4 minus x3. And this is the general way I can define my Lagrange operators. Okay. Now, in this case, if I use 3 data points, I come up with a quadratic interpolation. Okay, and then I will write f2 of x as a combination of fx1 plus fx2 plus fx3, and the weights of fx1, fx2, fx3 are L1 for fx1, L2 for fx2, and L3 for fx3. And then I say that it's a second order polynomial, and I can do an interpolation with any order I want. Okay, so let us do an application on Lagrangian operator to do interpolation. If I use a Lagrangian function, I will see that the results will be identical to doing a Newton. So expect to have exactly same results if you do Newton or Lagrange methods. Okay. But of course, what is the condition? Same selection of data, and you are working with same data points. with same order of data points. Please pay attention. So if you remember, last time we have set several criteria to decide on the points to select. So when you do Newton or Lagrange method, you do the selection in the same way to expect to have same results. Because if you are changing, if you are taking a different points or different order, even not only different points, if you have the same points but different order, you will get different results. Okay. So here we start with we want to determine what is f the interpolation at 3 fx3. So to do this, we'll select points. So here, as we did in Newton method, same approach. For linear method, we need 2 points. So we should define x1 and x2. Always we start with the closest point, so which is 2.3. And so this is point 1. As we said, when we select an odd number, so here the subscript is odd, it is the closest point. Now, when we select an even number, we should take the other side. And if point 1 was at left side, point 2 should be on the right side, even if is this point, which is on the left, is closer to 3. But the other the criterion when we choose an even number is to have a good distribution of points to the left and to the right. Because even if 1.5 is closer to 3, having 2 points from each side will give a better result for interpolating what will be f at 3. Okay. Now point 3, again, point 3, if you are doing a quadratic interpolation, we need a third point. Then point 3 has a odd subscript. So now I look at the closest one. So between 1.5 and 4.8, 1.5 is closer to 3, so it will be the third point. Now for the fourth point, since it's if I want to do a cubic interpolation, then I need 4 points. Here I will consider the other criterion because it's the subscript is even. So now I should consider the equal number of points distributed around 3. So this will be my selection. This will be my number 4. Now, in case I want to do a quartic interpolation, then I need a fifth point. And since it's an odd number, so I should take 5.2. Okay, because I should consider this point since it's closest to 3 than 0. So this will be my x5, and of course my x6 will be this 0.6. Okay, so in terms of selection of points, it's exactly the same method, so nothing has changed. Now, just if I want to use a Lagrange operator, the way of writing the function will be different. So I will write it. First, we will start with linear interpolation. So if you want to use linear interpolation, you should define your operator L1 and L2. So as you can see, as according to the definition, L1 is x minus x2 over x1 minus x2 times fx1 plus x minus x1 over x2 minus x1, which is L2 times fx2. You have everything, okay, because x1 and x2, this is x1. This is f of x1. This is x2. This is f of x2. And now your only variable is x. You replace by the point you want to interpolate at. So now you want to find what is your interpolation at 3. So all you have to do is to put f of 3, replace x by 3 here, and then you can get your value. And if you compare with Newton, you will see that it's exactly the same result. So if you are doing the two methods with same points and same order, and you obtain different results, this means that you have a calculation error. Okay. Now, if I'm using quadratic Lagrange polynomial, okay, then I will have the following. So f2 of x is equal to, so now this is L1. L1 is x minus x2 times x minus x3 over x1 minus x2 times x1 minus x3. This is L2 and this is L3. So here again, I have everything. So here I add, this will be my x3, and this is my y3. So what I have to do is to replace the numbers, and I replace x in the expression by 3 because I am interested into finding f of x at point 3. So f2 of 3 will be 150.65. Again, it's exactly the same result I got with Newton interpolation. Okay. So as we have seen, in both Newton and Lagrange methods will give us exactly the same result. The condition is to have the same data points with the same order. Now, if you remember when we talked about accuracy, we said that we expect that first increasing the order of interpolation will give better results, okay? But we should pay attention because increasing a lot the order of interpolation can bring bad effects. It can lead to oscillatory solution. This is why we don't recommend to use very high order polynomial fit. If we just limit ourselves to fourth order interpolation or fifth order, it would be acceptable. But this is an example here why very high order will not work, while especially it will work very good in certain regions, but in general, high order interpolation can lead to large oscillations, especially near the end points. So here, if you consider the function 1 over 1 plus 25 x squared in the interval between -1 and 1. You have the white line represents the exact function. And we want to interpolate this function using two different orders. We tried the fourth order interpolation and we tried the 10th order interpolation. So you know that when you want to do a fourth order interpolation, you need 5 data points. So we have considered first 5 data points, 1, 2, 3, 4, and 5. So as you can see here, we can come up with a fourth order interpolation using these points. We'll get the green curve. If we compare, of course, the green curve should pass by all data points. So at data points, 0 error. But in between, we have errors. But it seems that the error is acceptable. You have a maximum error here, but it's not a very large error. We can say that it's an acceptable interpolation. While if we do 10th order interpolation to try to enhance the results, what will happen is the following. So I will take now, since I want to do 10th order interpolation, I will need 11 points. Always the number of points is equal to the order plus 1. So if I want to do 10th order interpolation, I need 11 data points. So I will take, this is point 1, this is point 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 data points. I will use them to do a 10th order interpolation. And then what I can see here is that it's working very well in this interval. So if you compare here, you have nearly a perfect match for a zone, for the centered zone in the interval. But as I am close to the end of the interval, I see a high oscillatory behavior and I will get a very high error. So the error you get here is much larger than the error you got, the maximum error you got in in the case of fourth order interpolation. So you can conclude that sometimes it will bring a bad effect to use a very high order polynomial fit. This is why we don't recommend to use a very high order polynomial fit. Just we can limit ourselves to 4 fifth order interpolation. Okay. Any question on this? Yes.
بس نحن لما بدنا نعمل هيدي الكيرف
No.
نحن we want to find an unknown point بالنص، مش رح ننبش على point on the edge of the.
مش ضروري. إذا أنا طلبت منك يمكن كنت طالبة منك f of minus 0.9. أنا فيني أطلب وقت تعمل interpolation يعني فيهم يطلبوا منك any point in the interval. هدف الانتربولation is to allow you to predict the value of f at any point in the interval considered. اوكي؟
ايه بس ساعتها باخذ interval بيكون هيدي البوينت بالنص بصير accurate.
ايه هلا هي انتبه، هي شو قالوا لك in general يعني ما في شيء على طول هيك هن قالوا لك may lead to large oscillation especially، بس مش على طول على الاند. معك حق، اذا على طول نحن اكيدين انه هالاوسيليشن حيكونوا على الاند، ساعتها مثل ما عم بتقول باخذ اذا الفاليو بجرب انا بوسع شوي الانترفال. اذا انا I am interested ب values around the center it's fine، بس ما فيك تاكد على طول انه حيكون كثير منيح الوضع at the center. يعني لو if you are sure of this yes it's a good strategy، but هون قالوا لك may lead near the end points in general، بس ما فينا نكون اكيدين. يعني sometimes you can have also oscillatory behavior in between. It depends on the function you are using. Okay, so to be on the safe side because we have observed يعني هن اكيد وقتها عملوا جربوا يعملوا high order interpolation لقوا انه هالاوسيلاتوري behavior can take place anywhere but especially at the ends. But since we have a risk no need to go over it. Okay, يعني اصلا بدها computational time اكثر وعندنا risk of oscillation انه يكون عندنا high error so no it's not worth to do. Okay.
Doctor?
Yes.
The Lagrange it requires the same order it gives the same result. So إنه شو بنستفيد عن نيوتن يعني؟ ما فهمت يعني لازم يكون another method يكون عنده advantage بس هيدي ما عندها.
Look هلا هي sometimes بالcalculation of coefficients يمكن في يعني حسب ال programmation that you want to use. يعني فيك you can compare a number of operations to see which one is better. بس معك حق accuracy هن similar. Okay, but هي إنه it's a different tool. يعني just هون شوي computation of the coefficients كل ما زادت n كل ما computation على هول coefficient b بتصير ثقيلة أكثر. So maybe Lagrange might seem to you easier in terms of finding your polynomial. يعني ما بتضطر تجيب B1 B2 B3 B4. وكل ما زادت الان كل ما صار اصعب يعني بصير عندك البيز اكثر تجيبهم. Lagrange is simpler.
Yes doctor.
Okay.
دكتور
نعم.
إذا كان عنا مثل قبل بتيبل الإكزامبل، هلا نحن بنعمل الأوردر لحتى نقدر نستخدم كل البوينتس ولا هن بيحددوا لنا قديش؟
هون you mean this table?
No, the example that we did.
Okay. Yes أكيد بيحددوا لكم. هن بيقولوا لك how many points you want to etc. It will be specific.
Yes. Thank you, doctor.
Welcome. Any other question on this chapter? Okay, so this is chapter 17. As you can see, the chapters are short. This is why we have a lot of chapters. So now we will end chapter 17 and we will start a new chapter. So I will open a new session to start the new chapter, okay?